withhold that. We have the final talk of the session. Sahayanathan will talk about X-ray emission processes from the Knots of Kiloparsec scales, Jets of AGN.
Thank you. So I'll be speaking on the X-ray emission process from the radio-optical Knots of Kiloparsec scale jet of AGN. I know it's pretty long, it's not interesting, so I have a very short name, knots getting naughtier. So we will say how they are getting naughty. Okay, fine. So to start with, so the AGN jets are very well mapped in radio and optical up to kiloparsec scales, and if you are, it means there are some bright spots on the jets which call as knots. After the advent of Chandra, due to his excellent spatial resolution, we are able to resolve those radio and optical knots in X-rays. So we had the radio jets, radio knots X-ray counterpart of the radio optical knots. So now the question comes is, we know that radio and optical are generally by synchrotron emission process from a polar distribution of particle. Now the question comes, what is the process which causes my X-ray emission? So a simple explanation which already Herman has spoke about it is, let me take a knot, take the X-ray flux and radio flux and optical flux and extrapolate that flux. And if my X-ray flux lies below the extrapolation of the radio optical, then one can model this with a single synchrotron emission model with a broken power law, and you can say the X-ray can be probably by your synchrotron emission process. On the other hand, if the X-ray lies above the extrapolation of radio optical, then it demands a particle spectrum, a concave particle spectrum, which is unphysical, or rather often cannot produce it. So then it says possibly the X-ray emission may be due to a different emission process, say something like I inverse Compton, or probably a new population of electron which is responsible for the X-ray emission, which is not the same which is causing your radio and optical emission. Well, let me go to the first point, that the emission is by your different emission process, inverse Compton process. So at the kiloparsec scales, what are the possible mechanisms by which I can produce the X-ray by inverse Compton process? Is my synchrotron self-Compton, and at that scale the external photon field is, the dominant photon field is my cosmic microwave background, so it can be either synchrotron self-Compton or the inverse Compton scattering of my cosmic microwave background. Well, now we have to decide among these two which one is the right candidate to explain my X-ray emission. So people many workers did a very simple calculation to find out. What they did is, they assumed the delta function approximation for the emissivities and calculated an approximate analytical expansion for a synchrotron flux, SSE flux, and external Compton flux due to EC-CMB photons. And they assumed a power law distribution of particle which is responsible for the optical and radio and optical emission. So what they did next is, so let us say if your X-ray is by SSE process and your radio and optical by synchrotron process, so from these two expressions, from the radio map, I can approximately guess what is the size of the emission region. So that gives me a size of the R. So plugging R here and using these two equations, I can eliminate K, correct? So then I will get a relation between my delta and B. So this is the first delta and B relation we get, assuming my X-ray to be a SSE process and other by synchrotron. Next comes, let me take your radio optical to be synchrotron, and my X-ray is due to my external Compton process. Then again, just by dividing that, you can eliminate K, and again you get another delta B relation. So one delta B relation for a synchrotron and SSE process, another delta B relation for a synchrotron and EC process. And you can do even one more, that is considering the equipartition condition. So the equipartition condition actually relates to your normalization with B. So substitute this, replace the K here with this B, so again you get another delta B relation. So basically we are getting 3 delta B relations, and now we are going to plot this 3 delta B relation and see what is going to happen. So what they did is, it was by Tavicchio, so they did nicely, they plotted the delta and B relation, and they found for the source pk 063775 minus 752, this is the equipartition condition by your synchrotron, and the equipartition condition, we got two lines. One corresponds to gamma min of 1000 and another gamma min of 10. What they found is your SSC, where it hits equipartition, is at a much lower line. That means your delta is highly debeamed, and it expects a very large magnetic field. So they said this is unlikely. On the other hand, your EC emission nicely crosses the equipartition at delta equal to 10 and a magnetic field of -5. So they found this is pretty comfortable. So this conclusion was so convincing. At that period, we all strongly believed that the X-ray emission is by EC-CMB, and many workers. Sorry, I have not quoted everyone. Because there are dozens of people who used EC-CMB to explain the X-ray emission. I just quote a few, and Preeti also worked on it recently. So 2012 she wrote a paper, and so we are convinced that EC-CMB is a right emission process to explain the X-ray. And the story took a different turn after the advent of Fermi. Eileen yesterday talked about it. Eileen, Marcus Ganganopoulos and his collaborators, what they found is, they found if the EC-CMB is the right model to explain my X-ray, it predicts an excessive gamma ray flux. And they calculated what will be, can that gamma ray flux be visible by Fermi, and they found it is not. The gamma ray flux predicted by the EC-CMB is much above the Fermi upper limits. Upper limits. So they decided, so this is not a model, and the puzzle opened again. We don't know what was the emission process. And Eileen and the collaborator again suggested the second option, it's possibly the second population which is responsible for the one. Now when you go for this, so when you look into that, what it means is I have a polar distribution which is responsible for my radio and optical emission, and there is another high energy population which is responsible for my X-ray emission due to synchrotron process. So now this question is, this model means if you assume this picture, we can say these two populations cannot coexist in a single region, because if it's a single region, again you end up in concave spectrum, which is not possible. So what possibly the thing is, these regions are actually physically separated. So that means the two populations from a physically separated region. Following this, Liu and collaborators proposed a model for this two population theory. What they said is when a shock, if you see the shock does a asymmetric compression between the downstream and the upstream region. So as the shock pumps in the particle into the different region, the regions have different compression. So you can actually have a different distribution of particle. So they said that possibly can create a two population, and that one, by that they can explain the radio, optical, and X-ray emission. So, and alternatively there's another model which I was working on. So that's something like a shock jet with the sheared boundaries. So if I say the knot is by a shock, and at the boundary if there's a sheared layers, and we have seen that there are often, means you have seen many limb Brighton jets like MK501, and where they show the index also changes. So it's then possibly indication that there can be a different acceleration process happening at the boundaries. So that means in a knot, there can be a shock acceleration as well as shear acceleration. So considering the both two different regions, I can again produce a two population, and by which I can explain the X-ray emission. Now, well, this is the two population theory. Now let me come back to the, is that means EC process. Is it that EC can be absolutely neglected because EC cannot be possible, or only the two population theory is right? To look carefully into it further, we did an exercise. What is, well, sorry, this is the one. So if such features, physically separated region, they should be resolvable from the high resolution radio images, which was not seen till now, or possibly the such features are too compact to resolve in the radio. Now, going to back to the EC emission process. So let me see, is there any way I can explain the X-ray by the EC emission process? What I did is, so we had an radio and optical. We modeled by synchrotron emission, and is a corresponding SSC. Now I should put an EC process here, which should explain my X-ray but we shouldn't cross my gamma Fermi upper limit. So it puts two constraints. My EC peak will be either it should not cross my gamma ray and it should not be lower than my X-ray. Now this is upper limit in the external Compton peak frequency and lower limit in the EC peak frequency. Now again going back to the mathematics, so we did from the synchrotron flux and we can get the delta B relation. So for a given delta, I can say what is my B. Now putting the B back here from the synchrotron peak, I can calculate what is my break gamma. Plugging it back into the EC peak frequency, I can actually calculate what is my target photon frequency. So I did this for a set of Doppler factors for the upper limit and lower limit, and this is what we got. So to explain the X-ray emission by EC process, I need a target photon, which should fall within the range. This is a gamma, assuming a weaving angle of 5 degrees, and this is the target photon frequency. What it says is, my external photon frequency should be in radio. It is not CMB or should be in radio. Now the question happens is, what is the source of radio photons in that kiloparsec scale knots? So then, we looked into further, like anything can happen. Then, for example, if you see the radio map, we always see very small radio pockets. We are not very bright, but still radio pockets are there. Is it possible the knot is Compton boosting the faint radio emission from the pockets? So then we use this model and we took a small radio emission from the radio pocket, inverse Compton boosted it, and we got that we are able to explain the X-ray and making sure the peak doesn't touch my gamma ray. So now there are questions comes like, so we are still trying to figure out whether this model is, how much viability of this model, we are still going on. Thank you.
Martin, now.
Go back to your previous slide. You were to plot the CMB, the inverse Compton CMB on this plot. Where would it go?
Right. I agree. So I missed it in the last plot when I put this because, see, there is a freedom I have. Yes, you can always have the point is, I can jack up if I have a large delta, then I can't avoid my CMB crossing my Fermi upper limit. So now to reduce the delta, I can increase my radio flux, correct? So that I can reach my X-ray. So I have two keys to turn over to make sure my EC-CMB never reach up, but my radio can reach up to X-ray.
Sorry, I don't understand. How can you increase the radio flux? You're talking about something which has a constrained radio flux. You need to make the radio photon energy density be much higher than the CMB photon energy density. But you have a constraint on the radio photon energy density because you know what we actually observe. I think. Yeah,
I agree. There's a lot of confusion is there. So because one picture what I can assume is, so if you say the knot, normally that's why I took the radio frequency beyond the SSA break. So if you see the knot is normally generally your magnetic field is high. If I take a off knot region, the magnetic field can be low. So if I'm able to probably take a snapshot of a radio jet in a much lower frequency in megahertz, what I would see is possibly knots are darker, but the off-jet radios are brighter because the photons from there are not self-absorbed. So it is, of course, it's a fairy tale model, I agree. Yeah.
We should talk about this.
Yes.
So when the IC-CMB model was being firmly established in the mid 2000s, right. So you have showed this here. So the SSC was also considered. That was also one of the things that's the synchrotron self-Compton. That correct. The synchrotron photons will also be correct. So X-rays will not be the synchrotron itself. It will be inverse Compton scattering of the synchrotron photons in the jet.
Right. But
and so turns out what I remember is. What turned out was if for high Z sources, the CMB is more powerful and so IC-CMB won. But for low Z sources, SSC was still a pretty good option.
Correct.
So I was wondering here you are showing the SSC to be much lower than what you need. But you know, I mean, if the SSC has to explain the X-rays,
Right. For this source,
then that will not work. But I was just wondering, I mean, what is the cause for the SSC to be suppressed like that?
yeah,
I mean,
if you want to increase up, then I have to go away from the equipartition.
Okay.
Okay, I think that's a good closing remark in such a session. Let's thank all the speakers again for the session.